So the plan is now to have a look on the proof of the Cook-Levin Theorem. So let remind you what this is all about. So Cook-Levin Theorem shows that formula satisfiability is NP complete. And here the important thing is that this is our seed problem, so we cannot do it with reduction. This theorem is much more general, right? It says every problem in NP can be reduced in polynomial time to satisfiability. Here, satisfiability, to remind you, is I give you a CNF formula. Does it have a satisfying assignment? So we of course seen that SAT is in NP. So, because you can just check in a satisfying assignment if it exists. So, we need to prove that for every problem in NP, there is a polynomial time reduction, and it's completely a priori not clear how to do it. So, this theorem is pretty magical, and the proof is not easy. So, let's talk a little bit about what the plan of attack is. So the basic idea is to say, if you give me a problem that is in NP, what are you really telling me, right? So first you give me a Turing machine that is a verifier or a certifier if you want, right? Given an input and a proof, it can verify that the proof is correct. In the language of Turing, a non-deterministic Turing machine, you can just think about it as a Turing machine that can make decisions, right? Similar to NFAs, non-deterministic finite automata, right? So it's a Turing machine that in every step there might be several transitions it can take, and it takes one of them. Among all the ones that are allowable, it picks one of them somehow using an oracle or something like that. So that's the model we are going to think about here. And so we have a Turing machine. We have the language associated with this Turing machine, right? So for every input, M accepts this input. And the important thing is that it accepts it in polynomial time, and we are given this polynomial, right? We know that we have to run this Turing machine on an input of n bits for that long before it stops. By the way, it's not strictly necessary for the proof, but you can assume that the input alphabet is essentially binary, the tape is binary, except maybe for a special character for the end of the tape. Okay. So the input really, when I tell you that the problem is an NP, what I really do, I give you two parameters. I give you the Turing machine M and the polynomial P, saying, you have to run to this time. If I care about a specific input, right, a specific instance of this language, I also give you the input X, right? And really the question becomes, does M stops on input X after P of X steps, right? Now, if it was a regular Turing machine, a deterministic Turing machine, there was nothing to do, right? We will just simulate the Turing machine. It would take us P of X time, maybe, there would be an extra some factors, but it would be easy polynomial time, and we would be done, right? The problem, of course, is that this Turing machine M here is non-deterministic. As I said, it can make choices. And that's where things become hairy, because we would like to simulate it, but take into account those non-deterministic decisions. Okay, so we are going to describe a reduction, a polynomial time reduction, that computes from those three input parameters, M, X, and P, a SAT formula. It's going to be a very large SAT formula. It's still going to be polynomial size in all the parameters, but it's going to be very large, such that if M accepts X in polynomial time, namely X is in the language L, this happens if and only if the formula is satisfiable. The way to think about this formula is that this formula is essentially going to make sure that there is an execution of the Turing machines on the input X such that the Turing machine stops and accepts X. Okay. So the input is mx, x, m, and p, and we need polynomial time generate this formula that needs to be a CNF formula, and this is satisfiable if and only if m accepts x in polynomial time. And the basic idea is that this formula is going to essentially write down the execution of m, right? And the formula essentially, if the formula is satisfiable, the formula essentially would fill in all the details of the execution. Now, what is the basic idea? The basic idea is that, when I give you a formula phi, it has many variables, v1, v2, right, vm. And think about this now. When I ask whether a formula is satisfiable or not, really what I'm asking is guess the values of those variables for which the formula satisfies, right? So the satisfiability inherently have this guessing part of give me a guess for which the formula is satisfiable, which in fact fill the need for these non-deterministic Turing machines to guess what decisions to make whenever it has to make a non-deterministic decision. So that will be captured by the formula, and the formula would be quite complicated because it would have to essentially verify that everything is being done correctly. Okay, so I don't know if we live in a simulation, but Turing machine definitely live in the simulation. Which is a matrix. So let's think about the matrix. What is the matrix? The matrix is going to be a snapshot of the Turing machine after every step of the Turing machine, right? So initially, what happened at time 0, we have the input in the first row, and then the rest of the tape is blank. Now, the important thing is that we know we are speaking about Turing machine that run in p of x time, right? Then we are never going to access steps that are in the tape that are past this point. So really we need to look only on this portion of the tape. So now the tape is no longer infinite. So that's already good. And the second thing is that if we are thinking about time, if every row is going to be one snapshot in time, and we're going to have p of x steps, then we need at most this number of rows, right? And I mean, every row I'm going to write down this current snapshot of the Turing machine, right? Okay, so what do we need to write down, right? Well, we need to write the content of the tape, where the head is, right? If you, right, here's the head is here, this is the underscore, next time step. The second row is the second next step, and so on. So really, this is just all the snapshots of the tape, right? Now, you can think about it that in addition, we write for every row, what is the current state? Now, here's the big deal. The big deal is that if you think about those rows, right? So this is time snatch 0, snapshot 1, time snapshot of the machine, time 2, and so on. The snapshot changes only very locally, right? Essentially, if the head is here, right, if a head is in a location, then it can affect literally only the location below it, or to its right, or it's to the left, right? The location below it, it means just what is the value of this tape cell after we do this step. And the left and the right are affected because the head might be moving to these locations, right? So really, those rows are just copies of each other where you copy them and then you make tiny local modifications. Every step of the Turing machine is just a local modification, where of course what also changes is the state of the machine. So now what we're going to do, we can think about all the cells of this big matrix of the simulation, right? So if I give you the machine M, and I have X and I know the guess, I can just run the machine and fill up this matrix, right? And whenever I have to make a guess about which transition to do, I write here what guess I made, right? So I fill this matrix, and now we can, of course, easily verify this execution is correct. But of course, the question is, how do we do it with a SAT formula, right? So the idea is that we are going to, some of the variables, we're going to have variables that capture all this matrix, all the information in this matrix, right? So they're going to capture first what every cell value is, right? So input cells, we know what they are, and we can just outright just say this is the value specified specify this value of the variable in the formula. But all the other tapes, the vast majority of the matrix is unknown. So for each entry in this matrix, we're going to have a variable that says, what is the value of this entry? Then we're going to have a variable that says, what is the state of the machine in any point in time? Then we're going to have a variable that tells us, for this time t, where is the head? What is the location of the head? And so on, right? We're going to essentially define a vast number of variables that fully encode this execution matrix. And now what we're going to do, we're going to write a huge CNF formula. It's going to be huge, but it's going to be still polynomial size, such that it would verify that what's written in the matrix is consistent. Indeed, the ith row follows is indeed the result of executing the I-1 row. Indeed, in the end, the bottom tape of the machine, let's say, you're indeed in an accepting state, so the machine accepted the state. All the transitions that were done were legal, the tape changed in a predictable way, the head moved in a predictable way, etc. Right? Now, this is going to be very tedious, so it requires quite a bit of care to define the variables and define the formula and so on, but we will do it shortly. But once you're done, right? Because once you're done, you have this huge formula, and it will be satisfiable if and only if you can fill this entry in such a way that what you get is a valid execution of the Turing machine on the input that accepts, where this Turing machine, as we said, is allowed to make non-deterministic decision, like NFA. Okay, so the variable, let's start from the variable of the formula. So because we are going to use Boolean variable, because we are defining Boolean formula, so instead of having things like counters, we're just going to have Boolean variable for every possible value of the counter. And we will just require that one of them would be true. So for example, TBHI, right? So this is going to be a variable, a Boolean variable, which is the tape cell at position H at time I hold the symbol B. If this claim is true, this variable would be 1. If it's not true, it would be 0. So all those variables, essentially, if you look on a specific time I, this variable would be 0 except for one entry, right? And we're going to have this, this is a large number of variables, right? Because the location of the head can be somewhere between 1 and the polynomial of x. B can be one of the alphabet of the tape. Gamma is the alphabet of the tape. It's different than sigma, if you remember. And the time that we are talking about I can be also between 0 and p of x, right? So this is at least p of, if n is the length of x, right? This is at least p of n squared times the size of the alphabet, right? This is the number of variables of this kind, the t variables. This is a large number, but it's a polynomial, right? I'm taking a polynomial, squaring it. It's fine, right? So this will define a large number of variables. They just tell me the value of the tape in any point in time, right? So fill the matrix. Of course, we will need to make sure that those variables are initialized correctly. Okay, HI would be the head on the tape is at location h at time I. Again, 0, 1 variable, where it can be one only in one place during any point in time. Of course, we will need to enforce this constraint somehow. Currently, it's just a bunch of variables. Again, this number of variables is large. Again, it's quadratic. It's p to the n squared. This is the number of variables, right? It's large. Right, then we have SQI, which is 1 if the state of the Turing machine at time I is Q. Right, so, and finally what we are going to do, we are going to take the Turing machine and write down all the possible transitions, right? So it's a finite number, right? And for every possible, so we will enumerate the transitions, and there would be one first transition, second transition, so on, until the number of transitions in the machine, whatever it is, it's the number of transitions is smaller than the size of the input, right? Because the input also has to describe M. So for each one of those possible transitions, we will have a variable iji, which means at time I, we executed instruction j, right? So I'm going to treat the j transition in this list of transition. I'm going to call it an instruction, just to, maybe clarify when I really care about this and when I'm using transition for other meanings. So this is going to be, again, a Boolean variable for that. And again, the number of variables here is large, but, it's going to be polynomial in the input size, right? So number of variables is not great, right? It's this polynomial, but it's polynomial in the input size, where here I use this notation to just say, number of bits we need to encode M in a reasonable encoding. Okay, so we defined now a large number of variables, but it's polynomial in the input size, and now we need to specify, we need to connect those all those variables together, put a formula down that says those variables have to be assigned values that are consistent with the input that we have, consistent with the way the Turing machine works. And so to this end, we are going to use some basic building blocks. So of course, we are going to generate a CNF formula. So one basic tool would be to take intersection of variables, right? This would be the OR of variables, so this is all familiar. The third formula is a bit, the third building block would be a bit strange. It's, let's call it O plus. So the O plus of n variable, it's the formula that is true if and only if exactly one variable is true. Okay? So we need to, since we're going to create a CNF formula, we need to convert this into a CNF formula. So let's do that. So what we're going to do, we're going to take the OR of any pair of variables among those n variables. So the number of such, if we have m variables, this is going to be m squared, m choose 2 pairs, right? So we're going to go over all m choose 2 pairs. And for every pair, we're going to take the OR of the negation of the 2 variables and take the end of this, right? Now, if you have 2 variables that are 1, then there would be a choice of 2 variables, such as this clause would evaluate to false, and then this formula would evaluate to false. So this formula is true if and only if at most one variable is 1. We, of course, also need to ensure that there is at least one variable that is 1, but that's easy. We just take the OR of all the variables. And then the O plus is just this formula, and this formula is a CNF formula. Okay, so we can encode this formula. And to remind you, the reason why we need this O plus, if you look on the list of our previous variables that we created, most of those variables were indexed by time, and all those variables that are indexed by time, in any point in time, essentially only one of them can hold. So we need to essentially have a lot of these conditions encoded. Okay, so now is the plan of attack. we are going to define 12 formulas. Yeah, I know, it's a bit painful. We're going to define 12 formulas that are CNF formula and take their intersections over those variables we just defined, such that this formula would be satisfiable if and only if the original Turing machine would accept X in polynomial time. And so we need to specify those formulas, which we'll do next. It's pretty tedious, so let's take a break.